So let's talk about the periodic table a little bit, chemical symbols. So I've been sort of writing them, but we haven't talked about them yet. So a chemical symbol is just an abbreviation that we use to indicate the element or the atom of an element. So most symbols have one or two letters. The first one is capitalized, the second one is not capitalized. So, a lot of them have one letter. So like C is carbon, O is oxygen. But of course, when we run out of the single letters, then we have to have a second letter. So, osmium is OS. So be careful because you want the second one to be lowercase because OS means osmium. If I wrote them both uppercase, then I would be talking about oxygen and sulfur. So you got to be careful. Same thing with well, some of them obviously can tell it different. So make sure and make the second one lowercase. Don't make it a smaller capital case. Like I've seen people do this, like radon. Definitely make it a lowercase letter. Even if you normally print all in capitals, just take the time to put it in lowercase because it makes it clear. So one or two letters, the first one is capitalized. Some symbols are derived from other languages, like especially Latin. Let's look at, I think the next slide has some of those. So here's just some common elements: aluminum, bromine, calcium, carbon, chlorine. You can see that oftentimes they match. So like Cl, chlorine, carbon, chromium, Cr, cobalt, Co. Again, that's another one. Make the lowercase smaller so that you're not talking about carbon and oxygen. Interestingly, copper, Cu, comes from the Latin cuprum, so cooper. Maybe that's not right, but cuprum. Okay, fluorine, gold. That's another one that's derived from Latin. Latin word aurum or shining is gold. Helium, hydrogen, iodine. Iron comes from Latin. Ferrum. Fe is Latin. PB, I love this one. Lead, PB. PB comes from Latin plumbum, and who works with lead, or at least way back when, who worked with lead pipes? The plumber. So you can see where that comes from. Magnesium, don't get magnesium mixed up. Mn is manganese. Mg, oops, let me see. Mg is magnesium, so be careful. I see people getting those mixed up a lot. Mercury, again, hydrogyrum, that's kind of means shining water, I think, is mercury. Nitrogen, oxygen. Potassium, K. Calcium. Anyway, Ag, argentum, again from Latin. Sodium comes from Latin. Tin, I love this one. Tin comes from stannum. You may, there used to be ads for toothpaste that would say that, this crust has stannous fluoride. Well, stannous is just Latin tin, so it's tin fluoride that's in your, the fluoride that's in toothpaste is usually tin fluoride. Zinc. Another one that I love is tungsten. Tungsten is the symbol W. Tungsten. And that one actually came from a German word, Wolfram. And Wolfram actually in German was kind of had the meaning of tin devourer. I can't spell devourer. I can't spell that right. But anyway, tin devourer. It was an element that got in the way of mining tin, and they didn't know what it was. And so they called it wolfram, and it turned out later to be tungsten, and so they gave it that symbol W. Anyway, that's just some interesting history back then. And so do you want to hear a potassium joke? Okay. Do you want to hear a sodium joke? Nah. Just a little funny there. Okay. Moving on. All right. So like I said, the number of protons defines the element. So the number of protons is sort of set. However, it turns out that different atoms of the same element, they'll have the same number of protons, but they can have a different number of neutrons. So the mass number, and again, this is why I question it, the mass number is given the symbol A. The atomic number is given the symbol Z. Why didn't they give the atomic number the symbol A? I don't know. Anyway, atomic number Z, mass number A. A is, since most of the mass comes from the protons and neutrons, we can figure that the mass number is the total number of the protons plus the neutrons. So that's the other number that you see on a periodic table, although it's kind of an average, and we're going to talk about that in a minute. But we can represent by symbol, which is called a nuclide symbol, we can represent the atomic number and the mass number. And so we write the nuclide, it looks like this. Let me just go ahead and put it there. So sodium 23. So let's, if you have a periodic table, look at it. Sodium actually has, I got to look at it, it's got 11 protons. So sodium has 11 protons. So it's element number 11. And so if the total mass is 23, that means that it must have 23 minus 11 equals 12 neutrons. So again, 23 is the mass number, which goes up here, and the atomic number goes down there. Now, sometimes you might see a nuclide symbol that doesn't have the 11 here, but, you know, again, that 11 is defined by this element. So, you know, if I just wrote sodium 23, you still should know the number of protons because you can look on a periodic table and see. I need to I think there's a periodic table coming in the slideshow, so just bear with me and I'll point out some of the numbers on there when we get there. But anyway, this gives you all the information you need to know. There's 11 protons because it's sodium, and then the total number of protons and neutrons is 23. Now, you can't know that. It's not like a mind reading thing. You can't know that. You've got to be told somewhere. So if I told you, well, it's sodium 23, then you would know 11 protons and 12 neutrons. If I told you there's 11 protons and 12 neutrons, you would know it's sodium 23. And so there can be different mass numbers for the same compound. Now, notice that mass numbers and atomic numbers are whole numbers. If we look at the periodic table, you'll see that sometimes the numbers are decimals, and again, we'll talk about that, but these should always be whole numbers. And so this is called a nuclide symbol. So again, this just summarizes what I just sort of said. So neutral atom has to contain the same number of positive and negative charges, and so the number of protons will equal the number of electrons for a neutral atom. So if I told you that sodium atom had 11 protons, 12 neutrons, and if it's neutral, it also has to have 11 electrons. When the protons and electrons are not equal to each other, and we'll talk more about this in coming chapters, what happens is the atom becomes electrically charged, and it's called an ion. So an ion is an electrically charged particle. So what happens, and you may not know why, but we'll talk about that probably in the next chapter. Sodium, so let's go back up to my sodium. Sodium 23 has 11 protons, 12 neutrons, and 11 electrons. If something happened and one of these electrons got lost, which we'll talk about in a minute, now the number goes down. Now the protons and neutrons aren't equal to each other anymore. Since protons are positive and electrons are negative, since there's one more proton than electron, then this particle will become a positively charged particle because it has an extra proton. So a charged atom, the charge of the atom will equal the number of the protons minus the number of electrons. If you gain electrons, then the number of electrons will be more, and this will become a negative number, so it'll be a negative charge. And so atoms and molecules that gain that get some kind of charge are doing so by gaining or losing electrons. The number of protons always stays constant. So again, let's just look at it a little bit more. So it turns out that if an atom gains one or more electrons, because it has more electrons than protons, it will become a negative charge. Negatively charged particles are called anions. So the way I can remember this is it's a negative ion, anion. An anion is negative. So let's look at an example. A neutral oxygen atom with an atomic number of 8 will have 8 electrons. If it gains 2 electrons, which it tends to do, and again, we'll talk about how we can predict that in another chapter, so we don't need to worry about it now. But if it gains 2 electrons, now it has 2 electrons, 8 protons minus 10 electrons, an additional 2. It's a negative 2, so it's gained 2 electrons. It becomes an anion. If an atom loses 1 or more electron, they exhibit a positive charge, and it's called a cation. So the cation, you can remember it's positive because it has a T in it, which looks like a positive sign. So the cation is positive, the anion is a negative ion. So for example, like I just said a minute ago, a neutral atom, sodium, has 11 protons and 11 electrons, but if this atom loses 1 electron, it will have a positive 1 charge, because take the protons minus electrons equals the charge. When we write the symbol, the charge goes in the upper right-hand corner. So you can see here, goes up here. Now, technically, if you have a +1, you don't need to have the 1. You could just leave it, positive. Sometimes you'll see it like a 2+ or a 2 negative. I don't really care which way you do it, as long as both the charge and the number are there if it's more than 1. So let me tell you another joke. So 2 atoms are walking down the street, and the first atom says to the second, "Oh my gosh, I lost my electron." And the second one says, "Are you sure?" And the first one says, "Yes, I'm positive." So just think about that for a minute. Okay, moving on. So like I said, atoms can, if you have 2 atoms that have the same number of protons, they're the same element. And if you change the number of protons, it's a different element. However, the same element can have the same number of protons, but a different number of neutrons, and therefore a different mass number. If you have 2 elements that have the same number of protons, but a different number of neutrons, and therefore a different mass number, those 2 elements are called isotopes to each other. So for example, chlorine exists as 2 isotopes in nature. Now again, this is not something you can know. Why does chlorine exist as 2 isotopes? I have no idea. It's something that you look up and you know, or you're told. So just so you realize that there's no magic there. And so I'm just telling you that chlorine does in nature exist as 2 isotopes, chlorine 35 and chlorine 37. So let's write the nuclide symbol for chlorine. So let's just look at this. So obviously they have the same number of protons because they're both chlorine. Chlorine's element 17. So how many neutrons does this one have? Well, it has 35 mass number, protons plus neutrons, minus 17 protons will give me, 18 neutrons. Chlorine 37, therefore, has 37 minus 17 has 20 neutrons. So they have a different number of neutrons. Again, they have to have the same number of protons because they're the same element. So the number of neutrons, this is protons plus neutrons, and this is protons. So if you subtract, you get the number of neutrons. So if we're talking a neutral atom, both of these have 17 electrons. So let's not worry about the electrons for now. Anyway, both of these atoms exist. So there's one atom that weighs 35 AMU, one atom that weighs 37 AMU. This because this atom has 2 extra neutrons. This atom does not. And these are called isotopes for each other, of each other. So again, the number of neutrons is A minus Z. How many protons and neutrons do each of these have? I just did that for you. They both have 17 protons. Chlorine has 35. Chlorine 35 has 18 neutrons, and chlorine 37 has 20 neutrons. Most elements occur as a mixture of isotopes. There's very few of them that only have one isotope. For example, carbon. Carbon has 3 different isotopes. I'll just write them here. Carbon 12, carbon 13, and carbon 14. So if carbon has 6 protons, then carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons and 7 neutrons. And carbon 14 has 6 protons and 8 neutrons. I don't know, there's 3 isotopes for oxygen. I'm not sure what they are. Oxygen 16, 17, and 18 probably. Like I said, chlorine has 2 isotopes, bromine has 2 isotopes. A number of them have isotopes. So now, if you look at a periodic table, if I look at carbon, for example, the bottom number of carbon, and again, we'll look at the periodic table in a minute, but hopefully you have one in front of you. It says 12.01. So what that is the weighted average. And let's look at chlorine. Chlorine's a better example because, like I said, there's chlorine 37 and 35. And if you look on the periodic table, the number at the bottom is 35.45 AMU. There's neither of those numbers. It's kind of somewhere in between. So what happens is that the number on the periodic table is actually what's called the weighted average. And you can clearly see that in this case, if you know anything about averages, if I just had 35 and 37, what's the average of 35 and 37? You would take them and divide by 2. 36 is the average of 35 by 37. But the number that's on the periodic table is not 36, it's a little bit less than 36. Well, if you take an average like this, what you're doing is you are assuming these are equal weight, meaning half of everything is 35 and half of everything is 37, and so the average is 36. But that's not the case. For chlorine, it turns out that about 75% of all chlorine is chlorine 35, and about 25% of all chlorine is chlorine 37. So what this is a weighted average. This average is closer to 35 than it is to 37, because if you go out there and collected 100 chlorine atoms, 75 of them would weigh 35 and 25 of them would weigh 37. So you're kind of taking an average out of every 100 instead of just assuming everything's equal to each other. So that's called a weighted average. And it's based on the fractional or relative abundances of the isotopes. And again, the abundance of the isotopes is not anything you can predict, it just is. It's out there in nature and you can actually look them up. So let me show you an example. So here's boron. Boron has 2 naturally forming isotopes. And again, I have no way of knowing this except that someone out there told me there are 2 naturally forming. So all those investigations have been done. But so this is the information that you can find somewhere. So there are 2 isotopes for boron. There's boron 10. Let's see, if you look on the periodic table, boron has 5 protons. So there's boron 10, and boron is element, I got to look at my periodic table. Boron is element 5. So it has 5 protons and 5 neutrons. Boron 11 then has 5 protons and 6 neutrons. Oops, I can't write. 5 protons, 6 neutrons, 5 protons, 5 neutrons. Now that's neither here nor there. Remember that the mass number is approximately equal to the total number of protons and neutrons. Well, remember that protons and neutrons don't weigh exactly 1. So actually, the mass of the boron 10 atom is actually 10.013, and the mass of the boron 11 is actually 11.009. And again, those numbers are given to you. You couldn't really figure them out other than they'd be given to you. And the other thing that would have to be given to you is this fractional abundance. So it turns out that about just slightly under 20% of all boron is boron 10, and about 80% of all boron is boron 11. So right from the start, you at least should be able to look at these numbers and say, okay, well, the average of these two here should be closer to 11 than 10. So on the scheme of things, since 80% is 11 and only 20% is 10, my average, weighted average, should be closer to 11. So I definitely want you, hopefully, if you see that. If you don't see that, make sure and talk to me. This is a really good little simulation to show you how weighted averages work. I would highly recommend getting on there. I may do a short video using that simulation later to talk about isotopes, but it's kind of a fun thing to play around and get the idea of weighted averages. Anyway, let's move on. So to get the weighted average, so it's kind of like you're saying, I'm not doing one boron 10 and one boron 11. If you take the abundances, it's sort of like saying, okay, if I have 100 boron atoms, about 20 of them, or 19.9 of them, are boron 10, and 80.1 of them are boron 11. So that's why we multiply by these fractional abundances. So we take the mass of the first isotope times its abundance, plus the mass of the second isotope times its abundance, add them together, and you find it's 10.811. And if you look on the periodic table for boron, it's actually the periodic table that I have on Canvas, 10.81, so rounded to 2 decimal places. So the main thing to remember is that the weighted average takes into account of how much of each isotope is present. So it's not taking a straight old average, it's sort of taking an average of 100 of them, and the percent abundance tells us how many of each there are. And as we predicted, the average, the weighted average of these two is much closer to 11 than it is to 10. So you can kind of predict before you do, but you should be able to do this kind of calculation. So this class, in fact, is a weighted average, just to give you an idea. And probably many classes that you've taken are weighted averages. Some aren't, but in this case it is. And so in our class, exams, depending on if it's a hybrid or in class, are worth between 45 and 50%. In this case, they're worth 50% of your grade. Labs are only worth 20% of your grade. So exams count for more. So and you know this from experience. If you fail all your tests, but you get A's on all your labs, you're still not going to pass the class because your overall grade will be much closer to your test average than your lab average. So again, exams count more, and your weighted average should be closer to the thing that counts the most. In vice versa, if you get A's on all your tests but you don't come to lab and you fail, now actually if you read the syllabus you have to at least do some labs, but let's say you fail the lab, you could still pass the class because the labs aren't worth as much. Same thing with homework will be worth 15%, so that's not going to affect your grade, which a lot of students get upset about because you can do really well on the homework because obviously you're doing it on your own and you can redo it, and you can get really strong grades on that. But if it's only worth 15% of your grade, it's not really going to affect your overall average that much. So certain things weigh more. One bad test grade will bring your grade down more than one bad lab grade. So just keep that in mind. And that's how I figure out your grade in the class. So I'll take, in this case, if the tests are worth, like I said, 50%, and the labs are worth 20%, and the homeworks are worth 15%. Homework, and then the final 50, 60, 70, 80 are worth 15%. So I take whatever your test average and I multiply it by 5. And so the test average. And then I'll take your lab average and I'll multiply that by 0.2. And then I'll take your homework average and I'll multiply that by 0.15, and I'll take your final score and multiply that by 0.15. So just what I did on that previous slide, and when I add those all together, that'll be your average. So you can see that your test average will weigh more than the others. Okay. Let's just do one more quick example. Magnesium has 3 isotopes: magnesium 24, magnesium 25, magnesium 26. Again, you have no idea to know this, so this information is given to you. So the weight of one magnesium is actually 23.985. The weight of magnesium 25 is 24.9. So this gives you a much closer mass than these numbers. But if you weren't given these, you can use these numbers, 24, 25, 26. But most likely you'll be given these numbers. Here's the abundance. Almost 79% is magnesium 24, 1% is magnesium 25, or 10%, sorry, and about 11% magnesium 26. So right off the bat, you should note that probably the average should be closer to 24 than to 25 or 26. So we take the mass of the first one times its abundance. Make sure and use the abundance in decimal form. If you're given percentages, convert them to decimals first, or at the end, divide by 100 to convert at the end. But either way, if you're given percentages, make sure to convert them to decimals. So the abundance, the mass of the first one times its abundance, plus the mass of the second one times its abundance, plus the mass of the third one times its abundance. And you can see, again, we predicted it should be closer to 24, and it is. So most of the mass is from the 24. All right, so you should be able to do that. All right, so let's kind of move on and talk more about the periodic table. So you probably want to remember the names of those scientists that we talked about earlier, and the periodic table is Dmitry Mendeleev is actually the first scientist who kind of created the periodic table. Actually, another German scientist, Dmitry Mendeleev was Russian. There was another scientist, Meyer, just slightly after him, who worked independently and who came up with the same ideas. But they both discovered that if you start to arrange the atoms or the elements in order of atomic number, actually they didn't even know about atomic number yet, but they did it by mass number. And you'll see that actually there's a few little errors out there that might mess them up. But anyway, today we know that if you arrange them in terms of atomic number, because the neutron wasn't even discovered yet, so they didn't know about mass number, but they use the mass of the atom. Anyway, if you place them in horizontal rows, and that the elements, what happens is when you start to see patterns, and elements in the vertical column will have similar properties to each other. So sodium, lithium, and potassium are all elements in the first column. They all act very similar to each other. They're all shiny. They're all very reactive. They conduct heat and electricity. Everything in the second column acts very similarly to each other. If you look in column 17, which are the halogens, which is chlorine, bromine, iodine, fluorine, they all act very similarly to each other. They're all gases, and they are mostly gases or very reactive. Anyway, this is called the periodic law or the periodic table. So Mendeleev and Meyer used this pattern they were able to figure out where there should be spaces left for unknown elements. They would predict maybe that there was some element out there with certain properties that belonged somewhere, because the elements that were known didn't match the periodic table. You know what I'm saying? Let's see. So they may have known, here's our periodic table today. They may have known, this one and this one and this one, and they lined them all up. And then they say, wait a minute, there's instead of putting these next to each other, say, wait a minute, there's one element that should be here that we don't know about, and then put the next one here and say, wait, there's probably one out there that has certain properties, just like the one above it. So they were able to predict, in fact, I believe germanium was one element that wasn't known that they were able to predict in gallium. Anyway, let's look at the periodic table. So anyway, the tabular arrangement of elements in rows and columns, highlighting the regular repetition of properties of the elements, is called the periodic table. So there's periods, it repeats itself, repetition. So here's a modern day periodic table. So I was sort of talking about this earlier. And you definitely, I have on Canvas, I have a periodic table. It's a really, I like it. I don't love this one that I have up here on the slideshow, but I wanted to show it to you because you're going to have different ones. The one on Canvas I like to use a lot. And probably in other chapters you'll see why, but for right now it doesn't really matter. So this actually tells us a lot of information. So let's look at it. So the top number in this case, and we can look at different, you can look at different periodic tables, but most of them have the top whole number. You can see 3, 4, 5, 6, 7. That's the number of protons. So you can see here, atomic number is on the top, and if they're in a different order, there'll be some kind of key that'll tell you what everything is. So the top number is the number of protons. Then we've got the symbol, so the symbol for the element. Then we have the bottom number, which is the atomic weight. What's the atomic weight? It's the weighted average, like we were just talking about in previous slides. So here for boron, we said that the average was 10.811. That's the weighted average of all the isotopes. So again, don't get those confused. There is an isotope, boron 10. Boron 10, there is a specific isotope out there, and if I write boron 10 like that, I'm talking about a particular atom that has 5 protons and 5 neutrons. I can't write 5 neutrons and 5 protons and 5 neutrons to give us boron 10. But if I take all the boron on Earth and figure out what the average is, that's this number. So that's why we always use whole numbers up here, because this is representing one element that has a particular number of protons and neutrons. So that's why it's always a whole number. But this number down here gives you an idea of approximately how many neutrons there are. And you can't tell by looking at, here's carbon. I said earlier, carbon 12, there's 3 isotopes for carbon, carbon 12, carbon 13, carbon 14. You see here the average is really, really close to 12. So that turns out about 99% of all carbon is carbon 12, like 1% is carbon 13. So the average is much closer. So you can't tell by looking at these numbers, but this is the atomic weight or the weighted average. A couple other things to look at. So you can see here we have periods going across. This is the first period, the second period, the third period, the fourth period, fifth, sixth, seventh. It turns out, notice that these actually come down here. So 57 and then 58, 89 and then 90. So these actually fit in. If we sort of open this up, these actually fit in. Make this wider, but they tend to be put down here to make the paper smaller. Otherwise, it'd be real long. This one's really nice because it tells us, and we'll talk about this in a minute, metals, nonmetals, and metalloids. We'll talk about the properties of those. You probably already have an idea because you know what metals are. Anyway, all the blue ones are metals, many more metals. All the orange ones are nonmetals. And then the ones in between here, these green ones right on the borderline, are metalloids. They're kind of in between metals and nonmetals. This dividing line right here is the technical dividing line between metals and nonmetals. So silicon is technically a metal, nonmetal. Arsenic is a nonmetal, tellurium is a nonmetal, but we also have them as metalloids. Germanium is technically a metal or a metalloid. Notice that hydrogen is actually not a metal. It actually could go over here. It kind of belongs here and it kind of belongs here. And by the end of the semester, you'll understand why. A couple other things. So the names. So the main group elements. Oh, notice that in my periodic table that's on Canvas, which is the one that you'll probably, and if I give you tests, you'll have access to a periodic table. I'll probably staple it to the test, and it will be the one that I have accessible on Canvas. So that's probably the one you want to practice with the most. Mine actually has the name of the elements on it as well, because sometimes we don't know the symbol, and we need to know the symbol and the name. So I also have another sheet out there on Canvas that you can download that has all the names in alphabetical order and their symbols, so that can kind of help you get to know the periodic table better. Anyway, notice that there's two numbering systems. So there's 1 through 18, which is kind of the newer system. I actually like the older system, so you can see here's 1A, 2A. All these in here are the B's, and then 3A, 4A, 5A, 6A, 7A, 8A. So all these A groups, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, are called the main group elements, or 1 and 2, and then 13 through 18. All these B groups in here are called the transition metals, the ones in between here. And then the inner transition metals are these down here, the lanthanides and the actinides. So anyway, you can get a lot of information. Don't panic, because this will always be available to you for tests. But let's kind of move on. So let me tell you a little bit. So again, a period consists of all the elements in a horizontal row. That should say row. A group consists of the elements in any one column. Groups are numbered. Like I said, there's 8 A groups, which are the main groups, or sometimes they're also called the representative elements. The B groups are called transition elements, and then the other 2 rows at the bottom are called inner transition. I've already gone over these. Elements in any one group tend, now it's not absolute, but they tend to have very similar properties. We have some names of some of these groups. The elements in group 1A are called the alkali metals. They tend to be soft metals, and they react very easily with water especially, so they're usually stored under oil because they're very reactive. Elements in group 8A or group 18 are called the noble gases. They actually don't react with other elements very well, and so that's why they're called noble. The group 7A or group 17 are known as the halogens. You should know that name. They're also very reactive, and they're all nonmetals. So I would know the alkali metals, the noble gases, and the halogens. Group 2A are called the alkaline earth metals. So you probably want to know those, and you would want to know transition metals, inner transition metals. Now there's a few other names in the book that I can't even, like chalcochins or something like that. I don't care if you don't know those, but these are the groups I want you to know. So the noble gases, alkali, halogens, and alkaline earth, and then transition and non-transition, or transition and inner transition. Okay, so let's talk about metals, nonmetals, and metalloids. What is a metal? A metal tends to have the following characteristics. They tend to be lustrous or shiny. They tend to be good conductors of heat and good conductors of electricity. And they are ductile, which means they can be made into wires, and they tend to be malleable, meaning they can be flattened into sheets. So the metals are all on that periodic table are all the blue ones. Nonmetals then are elements that do not exhibit the characteristics of the metal. They tend to be more gases or liquids. They tend to be non-conducting. You can't make wires. You can't make sheets out of them. They're very poor conductors of heat and electricity. And then, of course, your metalloid will be something in between. So they tend to be semi-metals or they have both metallic and non-metallic properties. And interesting, if you look at the periodic table, things like silicon and germanium, those are 2 elements that are metalloids. And you may have heard Silicon Valley. Silicon Valley, you know that's where they make a lot of computer chips. Silicon and germanium tend to be really good elements in computer chips, and the reason they are is because they are, as you've probably heard the word, semiconductors. They're not like metals where they're very good conductors where everything would fry out, but they're not poor conductors because they're non-metals, so they're actually somewhat in between. They're semiconductors, and that's they're slow enough that they can pass electricity, but not so slow that nothing gets done. So that's kind of an interesting thing. All right, so that's it about the periodic table. Again, I would definitely pull up the one that I have on Canvas and take a look at it, get familiar with it. I've got all the mass number, the atomic weights that I have on there, or atomic masses, are to 2 decimal places. Some have more, but that one just has 2. So anyway, let's talk about chemical formulas. What's a chemical formula? We've already written a few of them, like CO2, H2O. You're already familiar with those. So a chemical formula is just a notation using the atomic symbols and subscripts to tell what the relative proportions are. So, like I said, CO2, let's write that there. Yeah. CO2 just tells me that I have 1 carbon and 2 oxygens. H2O tells me that I have 2 hydrogen and 1 oxygen. So these are the element symbols. When we combine them together, it tells how many are in the compound and the ratio. Remember that in compounds, the ratio is constant. Here's another formula. Aluminum oxide is a element, or sorry, a compound that has 2 aluminum for every 3 oxygen. And so this is the ratio in this compound. So that's a chemical formula. Molecular substances, we talked about this earlier, but so we have compounds. So we have elements, which are atoms, and now we have molecules. Molecules are atoms that are a group of atoms that are chemically bonded to each other. And later in the semester, we'll talk about how they're bonded together. But in other words, a bond is a tightly connected attractive force. So there's different kinds, and again, that will come later in the semester. It's unfortunate you kind of have to know certain things to learn chemistry, but then we don't explain it totally till later on. But everything will get explained in time. You just kind of have to know a few certain things right now. So a molecule so a compound is generally a molecule. So a molecular substance is a substance composed of molecules, which are all alike, compound. The molecular formula then gives the exact number of each type of element in the molecule. A structural formula is how the atoms are bonded to each other. So as we go through the semester, we'll start looking at how atoms are bonded to each other. But you might see some of those pictures now, and just so you know what they are. I did want to point out, I talked about this in the last PowerPoint. So most molecules is a group of atoms, and most of the time there's more than one element. So like I said, CO2 has 1 carbon, 2 oxygen, etc. And just to point out and to remind you again, there are 7 elements that are also molecules. So like hydrogen only exists as a molecule H2, even though it's an element. So compound has more than 1 element, but this is still a molecule because there's 2 hydrogen bonded to each other. Oxygen, nitrogen, hydrogen. I already did hydrogen. Chlorine, bromine, fluorine, iodine. Oops, that's a 2. 1, 2, 3, 4. There's 7 of them. Yep, those are the 7 elements they're elements and they're molecules because there's 2 of them combined together. So we'll look at this later, but it's sort of like 1 hydrogen and 1 hydrogen bonded together. Just keep that in mind. All right, so here's formulas. So here's a molecular formula for water, H2O. Here's a molecular formula for ammonia, NH3. That tells you there's 3H to 1N. Ethanol is C2H6O. These are structural formulas, which we'll get to near the end of this semester, just showing what things are bonded to what other things. We actually have a ball and stick model. This is a model, so it's kind of a 3D space filling shows you what the shape of the molecule is. This shows you with the ball and stick, so this is not as accurate as terms of its shape. And this is called a space filling model down here. Anyway, you might see some of these along the way, but just realize that this line here just means there's a bond between those elements. But probably for right now, these are the molecular formula is what we'll use. Oh, here's what I was talking about. So most elements do consist of discrete individual atoms, most elements, but like I said, just to remind you that some elements do exist as molecules. Here's those 7 that I told you about. Sulfur actually usually exists as S8, so if you write down sulfur as an element, usually you would write S8. And just to, again, to show you the difference here. So here's one hydrogen atom. Here's 2 individual hydrogen atoms. Here's a hydrogen molecule where the 2 atoms are stuck together. And then just to be complete, here's 2 complete hydrogen molecules. So kind of keep that, they're all different, and well, this is the same, but that's just 2 of them. These are the same, but that's 2 of them. But don't get confused 2 hydrogen atoms from a hydrogen molecule. And this is how it exists in nature. So I'll try to keep reminding you of that till we get into it, explaining it more. And like I said, we can also have structure. So here's the structure of some of those. That's just showing how the bonds are. And by the end of the semester, you'll be able to do this. But there's something called an empirical formula. So an empirical formula is just the simplest whole number ratio of atoms or ions in a compound. So and then compare that to a molecular formula. Molecular formula is what we're used to. That's what's actually in a molecule. It's the actual number of atoms. It's important to distinguish them because you will see when we start doing the next topic, we're going to end up with empirical formulas and we have to know the difference. But just for an example, I think it's very easy to understand. A molecular formula, so benzene, the molecular formula for benzene is C6H6, and that's what benzene looks like. It's got 6 carbons bonded with 6 hydrogens, 1 bonded to each carbon. Here's acetic acid, C2H4O2. And that's the molecular structure, that's the molecular formula. The empirical formula, like I said, is just the lowest ratio. So the empirical formula for benzene is CH. It doesn't mean the molecule only has 1 C and 1 H, it's just telling us the ratio. There's 1 C for every 1 H. The acetic acid has an empirical formula of CH2O, so that's the lowest ratio, 1 C to 1 O to 2 hydrogens. Now, notice that these are just multiples, so this is a multiple of 6. There's other molecules that have the same empirical formula. So like there's acetylene is C2H2. So that has the same empirical formula, but it's a molecule that looks like this. It's got 2 carbons bonded to each other and 2 hydrogens. So anyway, note the difference between a molecular formula and an empirical formula. Empirical formulas aren't really real. They're just the lowest ratio. And of course you can have, if you had a molecule like CH4, this is the molecular formula, and what's the empirical formula? Well, it's also CH4, the lowest ratio. So sometimes the empirical and molecular could be the same, but the molecular could be any multiple of the empirical.